Okay, so let's talk about free body diagram. Now, free body diagram is an incredibly useful and important tool for doing the force and moment analysis. You will need this in time and again in different classes, not just 101. Right? So if you learn this well now, you'll see that you will have a much easier time in statics, in dynamics, as well as kinematics class. Right? So what is a free body diagram? Free body diagram is nothing but a visual illustration or a pictorial tool for showing all the forces and all the moments that act on an object. Now, that object could be just one particle, one thing, or it could be a system of particles, multiple things together. Now, it is not just a picture. Let me remind you, free body diagram is not just a picture that you draw. Free body diagram is something that you will use to do all the analysis after that. So if your free body diagram is wrong, all the analysis is going to be wrong. And if your free body diagram is correct, it's just a mechanical process to get to the final answer. So this is the key step to doing the force and moment analysis, being able to draw a free body diagram correctly. And the good news is that it's not difficult to learn that. Right? As long as you pay attention to the details, you will see that you'll be able to get it. Right? So let's start with an example. Right? This is a picture I showed you guys in the last class as well. Right? A girl is pushing on a car. What are the forces acting on the girl and on the car? Gravity. So gravity is pulling both of them down, right? Gravity is pulling the girl down. Gravity is trying to pull the car down. Any other forces? Friction forces between the car and the ground. Friction forces between the car and the ground. Normal forces. So the forces that the ground is applying on the car and on the girl, right? Because if somebody is standing on something and if it's being supported, that means there has to be a supporting force. That's the normal reaction he's talking about. On the car, right? That's true. So you also have the force that the girl is applying on the car. So there's a force of push on the car by the girl. Friction force on the ground between the girl and the ground, right? So there is a friction force between those two as well. Car is pushing back on her, right? So that's the Newton's third law. If there's a 5 Newton force being applied by the girl on the car is applying the same force on the girl in the opposite direction. Air resistance, of course, you have air resistance as well, right? You have air resistance as well. Anything else? Friction between the girl and the car, right? So if let's say the hands have to stay on the surface of the car, then there should be friction. Otherwise, it's going to probably slide, right? So there's friction between the girl and the car as well. Any other forces? You guys have pretty much accounted for all the forces, right? But here's the thing. When you solve problems, you don't necessarily show all the forces. There is something called reasonable assumptions that you make. Most of the time, we neglect the air resistance. Okay, unless the problem is talking about, an object moving through a fluid, so maybe an object dropping through the air or moving through water, we don't talk about the drag forces from the fluid medium. At least we won't be concerned with those forces in this class. So air resistance is not something that we'll have to worry about. Okay, not in this class, right? If you take a fluid mechanics class, you will definitely be worried about the drag forces from the fluid medium. We will also sometimes neglect the friction forces. So for example, we might say that, hey, if the car is rolling smoothly on this incline, there is no friction force between the ground and the wheels, right? In some cases, it will be very, very clear when you should take into account the friction forces. For example, if you have, let's say, a two-wheel drive car, right? And it's a front-wheel drive car. Then the torque from the engine is being applied on the front wheels only, which means that there will be friction forces on the wheel from the ground on the front two wheels. But your rear wheels are not driven by the engine, so you neglect the friction forces from the ground on them, because there is no traction available to the rear wheels, right? And that's why, when you drive your car in snow or in conditions when things are kind of slick on the road, then you prefer to have an all-wheel drive. Why? Because all the four wheels can have traction or the friction from the ground. Right? So in that case, if somebody tells you we have an all-wheel drive, by all means show the friction forces on all the wheels. But if, let's say, none of them are being driven, like in this case, if nothing is being driven, you can say, hey, I'm going to neglect the friction force on the wheels from the ground. Now, what about the friction force between the ground and the girl's feet? Can you neglect that friction? You can, right? Because if she's going to be pushing on this car in the forward direction, and the car is going to be pushing her in the backward direction, then she needs to have friction so that she can hold her place or move forward, right? Otherwise, she's going to skid down. So that friction cannot be neglected. So there are certain forces that we will definitely show. There are certain forces that we will choose to neglect, and we have to state that in the assumption. Another assumption that we make in engineering is the assumption of a physical object idealized as a particle or as a rigid body. So what's the difference? A particle in engineering is not a mathematical particle. We deal with what are known as engineering particles. Engineering particles have mass, but they have no size or shape or volume. So we can idealize physical objects as point objects, as points. You will just show them as a point, but they have mass. And it's an engineering particle. It's not a mathematical particle. Mathematical particles are just points. They don't have any mass. Most of the time, if you have no rotation involved, if you have just a translation, things moving, where all the points are behaving in an identical fashion, you can regard physical objects as particles. And you will see, that in your engineering statics and dynamics class. But if things rotate, you can not generally regard them as particles. Right? And particle assumption has nothing to do with the size of an object. You can treat a spaceship, a satellite, and an aircraft as a particle. If you are only interested in its gross motion, for example, if I said, hey, find out the time it takes for an aircraft to travel from New York to, let's say, New Delhi. Okay? You don't worry about how much of the wings are fluttering while it is moving, right? You just regard it as a particle, which has a certain mass. And you apply your kinematics equation to find out how much time it would take for it to get from New York to New Delhi, right? On the other hand, if you're interested in finding out how much wings really flex while it is going through the turbulent weather, because you're trying to design the wing geometry, then you cannot regard it as a particle because you have to take into account the rotation, right? So depending on your application, depending on the sort of problem you're trying to solve, you can regard a physical object as a particle or as a rigid body. In this class, most of the time we will neglect the rotation. Okay, so most of the things can be regarded as particle, but there will be a situation where we won't regard things as particles. So we will actually treat them as a rigid body object, and we will have rotation as well. So coming back to this example, what we will do is we will regard both of these physical objects, the girl and the car, as particles. So even though I'm showing them completely, you could just choose to draw a dot and show all the forces going through that, right?